Bismillahirrahmanirrahim. We now on chapter 5 or chapter 19 according to our textbook, entitled as the first law of thermodynamics. In previous lesson, from chapter 1 up to chapter 18, okay, covering from physics 1 up to almost half of physics 2 already. Basically, we are talking or involving dynamics part, where we involve motion, work done, acceleration, friction, any kind of dynamic parts, okay, involving mechanical parts only or concept. We haven't taken a look on the thermo part causing the dynamics, right? So now for this chapter, we are going to take a look on the first law of the thermodynamics. How the the heat, going to cause the dynamics, motion, work done, force involves, pressure, so many things. So basically the idea is we are going to use equation 8.2, which is conservation of energy. If you still remember, it's delta K plus delta U plus delta E internal equivalent to work done on plus heat plus transfer of mechanical wave plus transfer of electrical transmission plus transfer in terms of matter transfer plus transfer in terms of electromagnetic radiation. So we are going to use this equation again, conservation of energy, but somehow we are going to simplify or reduce this equation into the first law of thermodynamics equation. So basically in this topic, okay, we are going to observe gas within defined volume. Okay, we are going to take a look what will happen if there is force applied to the gas, there is heat supplied to the gas, must be some changes to the temperature, volume and pressure of the gas. How is it related to the equation of conservation of energy here? So before we proceed with any other things, okay, we need to have a clear understanding and be able to differentiate between heat and internal energy, because this is going to be used a lot in this topic, right? So what is internal energy? Internal energy is all the energy of a system that is associated with its microscopic components. What is the microscopic components? Atoms and molecules. When viewed from a reference frame at rest with respect to the center of the mass of the system. So any kind of energy related to the microscopic component. So means that, right, if we are referring this in simple manner, let's say we are talking in math language. Okay, you have a set. Within this set, you have a lots of subset. Okay, the whole set here is E total. Okay, for the bulk energy, the total energy contained within the system, right? So you have subset. Combination of the subset give you the total E or set, right? So within the subset we have potential energy, we have kinetic energy, we have bonding, let's say, okay, we have heat, okay, what else, many other kind of energy. So combination all of this subset or type of energy, right, will give us the E total of the system. So this is the meaning of internal energy. It's everything within the set, okay, consists of all subset, right? This is the meaning of internal energy. Right now, what is heat? Heat is defined as a process of transferring energy across the boundary of a system because of a temperature difference between the system and its surrounding. It is also the amount of energy Q transferred by this process. So from here, the one that can move in and out from the system is Q. Okay, Q can be transferred in, can be transferred out from the system. Okay, the amount of energy that can be transferred into or out from the system is defined or named as heat. Okay, so this is a process of transferring, right? Heat is defined of the process transferring of energy across the boundary. Okay, so the symbol is Q, right? So this is the difference between internal energy and heat, right? So units of heat, okay, a very beginning from the scientists doing the experiment about foods being used up is calorie, right? Is calorie, the symbol is CAL. Right, energy, it means that energy transfer necessary to raise temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius at the atmospheric pressure. So calorie here, the big C here, okay, is equivalent to 1000 of these calories. So the one that written in our packaging of foods, actually this one, okay, times 1000 of this calorie. And we have another option where we have British Thermal Unit, BTU. Okay, this is normally used by the US as a US customary system or units. Okay, it means the energy transfer required to raise temperature of 1 pound of water from 63 degree Fahrenheit to 64 degree Fahrenheit. It almost the same concept, it just different approach. Previously, the early scientists think that mechanical energy and heat are two different type of energy. They cannot have a relation how mechanical can convert it into heat or vice versa. Actually, we can do conversion, or we can relate between mechanical energy to heat. So let's take a look on this example. Okay, we have hammer and nails. Okay, we are going to hammering the nails, okay, into a scrap piece of wood here. So what happened to the all kinetic energy of the hammer once we have finished? Okay, for the nail and board as a non-isolated system, alright, equation 8.2 just now, okay, the conservation of energy that I showed you in the early slide just now becomes this one only. Delta E internal equivalent to work done on the system plus transfer of mechanical wave. Okay, where transfer of the mechanical wave here is the energy leaving the system by sound wave when the nail is struck. Okay, and delta E internal here represent the warmer nail and wood after you hammer the nail. Right, notice that there is no transfer of energy by heat, okay, in this process actually. Although this connection between mechanical and internal energy was first suggested by Benjamin Thompson, it was James Prescott Joule who established the equivalent of the decrease in mechanical energy, right, and increase in the internal energy. So this is the mechanical energy, this is the internal energy of the system. Okay, let's take a look on the schematic diagram of the Joule's most famous experiment, okay, which is this one. The system of interest is the earth surrounding, the two blocks, right, and then the water within the thermally insulated container, Okay, what is done within the system on the water by rotating paddle wheel here, right? Which is driven by heavy block, two heavy block with mass M. Okay, falling at a constant speed, right? The energy transform in the bearing, okay, and the energy passing through the wall by heat are neglected. So we consider there is no heat transfer within this container, okay? Okay, after the block and pedal stop moving, right, the decrease in gravitational potential energy during the fall, okay, of the block equals to the internal energy, okay, or internal work done by the pedal on the wheel on the water, and in turn the increase in the internal energy of the water. If two blocks fall through distance h below, okay, the decrease in potential energy of the system will be 2 mgh, where m is the mass of the block. This energy transforms to internal energy, E internal, right, of the water. By varying the condition of the experiment, Joule found that decrease in mechanical energy is proportional to the product of the mass of the water and the increase in water temperature. Okay, this proportional constant was found to be approximately 4.18 joule per gram dot degree Celsius. Okay, it means what? It means, okay, for 1.8 joule of mechanical energy raises the temperature of 1 gram of water by 1 degree Celsius. So further experiment, more precise measurement being done, that latter demonstrated the proportionality to be is actually not only 4.18 but to be exact 4.186 joule of energy needed to raise, okay, 1 kilogram of water by 1 degree Celsius. Therefore, 4.186 joule is equivalent to the 1 calorie, because 1 calorie also defined initially as the amount of energy needed to raise temperature of 1 kilogram of water by 1 degree Celsius. So this one we call it mechanical equivalent of heat. You have to memorize this one, okay? It's not given in exam or test. Example 19.1. A student eats a dinner rated at 2000 calories. He wishes to do an equivalent amount of work in the gymnasium by lifting a 50 kilogram barbell. How many times must he raise the barbell to expend this much energy? Assume he raises the barbell 2 meters each time he lifts it, and he transfers no energy when he lowers the barbell. So as we know, the delta U total is equivalent to W total. And delta U is equivalent to mgh because the student right now is lifting up, okay, the barbell. So now the delta U must equivalent to mgh times with the number of the repetition n. Okay, where we can have the delta U is equivalent to W total. So the number of repetition must be W total divided by mgh. So you have the W total to be done is 2000 calorie, must be converted into joule firstly. So because this is a big C, first thing first, you need to convert it into small c, and then after that convert it into joule. Okay, divided by m, g, and then h. So you have 8.5 54 times 10 to the power of 3 times. Okay, that is why the title of this example, losing weight by the hard way. Right, good luck for this person. Specific heat and calorimetry. This is subtopic 19.2, right? So if system consists of a sample of substance, let's say for this case water, for this case copper, right? Okay, this system and this system will have a different amount of energy needed to raise the temperature of our substance. It depends on the amount of the substance as well as the type of the substance. Okay, for example, okay, if we want to raise 1 kilogram of water by 1 degree Celsius of temperature, okay, we need 4186 of joule of energy, okay, to do so. But okay, if we want to raise 1 degree temperature, 1 degree Celsius temperature for 1 kilogram copper, okay, we only need 387 joule, okay, of energy, right? So it depends on the type of the substance, means that. Okay, so what does that mean by 4186 joule, 387 joules just now? We call it as heat capacity. Okay, heat capacity here, the capital C here, okay, is defined as the amount of energy needed to raise the temperature of that sample by 1 degree Celsius. Okay, from this definition, okay, we see the Q produces a change in the temperature, okay, of a sample is equivalent to Q equivalent to C delta T. Okay, how is it happen? Actually, it's coming from this. Based on an experiment, it is figured out that Q is directly proportional to the change in temperature of the system. So if you want to convert it into mathematical expression, you have to have a constant. The constant is the capital C, known as the heat capacity, right? So now, okay, the one we are used to is small c, right? Okay, what is small c? Small c is specific heat. Okay, specific heat, whenever we have, okay, the capital C just now over M, which is equivalent to small c. Okay, small c named as specific heat. Okay, so it means that what we have in our hand just now is Q capital C delta T, divided this into M, with M both sides, with the mass of the substance that we have. Okay, so we have Q and represent capital C over M is small c. So Q over M is small c delta T. So if we rearrange this, okay, Q equivalent to MC delta T, small c, small c. So the small c here, okay, also can be rearranged and put it like this. This is what we call it specific heat, because the capital C is heat capacity, but for small c, it's specifically over the mass of the substance, right? So we have the common equation that we use to, which is Q equivalent to MC delta T, actually coming from this concept. So if let's say we want to raise half kilo of water by 3 degrees Celsius, so we are going to use 0.5, the small c, specific heat capacity, 4186 joule per kilogram dot degree Celsius, times with a delta T, which is 3 degrees Celsius. Then you have this amount. So means that this is specifically the story when it is over the capital C over M. Okay, so examples, let's say we are heating or cooking potato in microwave. Okay, so what will happen to the system, okay, on our potato? there is change in internal energy in terms of transfer of electromagnetic radiation coming from microwave, which is causing the raise of temperature, which is means that causing the potato is being baked by receiving the Q, which is equivalent to MC delta T. And then next example is bicycle pump. So what will happen? There is change in internal energy of our system when we use the bicycle pump. Okay, by what? By the work done. Okay, on the pump. Okay, causing what? Okay, causing the heat being received by the pump, which is in terms of MC delta T. So if you refer to this table, you have specific heats, okay, of some substance at 25 degrees Celsius at atmospheric pressure. So you can see here lots of information, different according to the type of the substance. But the highest is the water. That is a sunnatullah, right? Because more than 70% of this earth is actually water. So even though we receive the heat from the sun quite numerous, right, still the water is actually stable because it is lots of energy needed to raise temperature of water. That is why we have earth as our home, okay, the best planet ever created by Allah Ta'ala. And now calorimetry. Calorimetry is actually a system, okay, where we are dealing or how to handle the heat, okay, that we discussed just now. So based on conservation of energy, okay, this is very common to you. Okay, Q cold must equivalent to negative of Q hot. This is actually coming from sum of Q must equivalent to 0. Okay, why is it negative of Q hot? Negative here because the Q hot going to transfer the energy out from each system. And please remember, recall back, the heat going to move or transferred from hot object to the cold object due to the temperature gradient or different. This is sunnatullah, right? So if you see here, we have a schematic diagram. We have isolated system boundary here. We have our hot sample where it has mx, cx, tx, and we have cold water. Okay, what will happen? Due to the temperature gradient, the energy going to be transferred from hot object to the cold object due to the difference in temperature between these two materials. Okay, so what are we doing here? This is Q cold, this is Q hot, right? And okay, if you transfer it, this is Q cold, this is Q hot, right? So negative of it. So when you substitute into this equation, you will have this kind of. So calorimetry is the process of calculating, we can say that. And now example 19.2, fun time for a cowboy. A cowboy fires a silver bullet with a muzzle speed at 200 meters per second into the pine wall of a saloon. Assume all the internal energy generated by the impact remains with the bullet. What is the temperature change of the bullet? So as we know, delta K plus delta E must equivalent to 0. Okay. Delta E internal equivalent to MC delta T. So change in, it means that kinetic energy final 0 minus kinetic energy initial plus the delta E is equivalent to MC delta T. So rearrange the equation. Our interest is right now to solve the delta T. So you will have here 85.5 degrees Celsius. Okay, suppose the cowboy runs out of silver bullets and fires a lead bullet at the same speed into the wall. Will the temperature change of the bullet will be larger or smaller? Repeat the same calculation, but replace the C here for lead. Okay, you will have a different answer. Okay, example 19.3. 0.05 kilogram ingot of metal is heated to 200 degrees Celsius and then dropped into calorimeter containing 0.4 kilogram of water initially at 20 degrees Celsius. The final equilibrium temperature of the mixed system is 22.4 degrees Celsius. Find the specific heat of the metal. So we are using Q hot, negative of Q hot, equivalent to Q cold. Right, so rearrange the equation again. Okay, and then you will have your C, our interest. And bear in mind, when you are using this, okay, negative MC delta T. Within the delta T, it's always T final minus T initial. Okay, that is for cold material. Always bear in mind delta T equivalent to T final minus T initial. Don't simply change this one, okay? The negative sign play the roles there. Then you will have your Cx equivalent to 453 joule per kilogram dot degree Celsius. Okay, so if you figure out the C is 453, okay, from here you're going to refer to table 19.1. Which one is the nearest to the 453? Okay, most probably iron. Right, most probably iron. This is the closest. So we can guess that this must be possibly iron. So now suppose you are performing an experiment in the laboratory that uses this technique to determine the specific heat of a sample, and you wish to decrease the overall uncertainty in your final result for Cx. Of the data given in this example, changing which value would be the most effective in decreasing the uncertainty. Alright. The largest experimental uncertainty is associated with a small difference in temperature actually, okay, of the 2.4 degree Celsius for the water, right? So what is the smallest that can be read from the scale of temperature? It must be smallest decimal place that can be read, which is 0.1 degrees Celsius. Okay. For example, we are using the rules of propagation of uncertainty. Okay, uncertainty for 0.1 degrees Celsius, okay, in each of T final and T W leads to an 8%. How is it? 0.1 over the reading. This is the uncertainty over the reading is equivalent to 0.04. Put it in terms of percentage is 4%. This is only for water. Okay, how about the other one, which is wood, right? So another 4%. Okay, so you will have propagation of error in terms of 8%. Okay, so for this temperature difference to be larger experimentally, the most effective change is to decrease the amount of water. So because water contributes so much of the percentage of the error or uncertainty. In previous section, we've learned that if there is heat transfer to a system, the system going to experience change in temperature. However, not all of the cases we can observe change in temperature. That is the case of latent heat, we call it. So this is subtopic 19.3. Latent means that hidden heat. Why is it hidden? Because the heat being transferred does not causing any change in temperature where we can observe clearly. Right, so L is the latent heat. Okay, it vary according to the type of the substance. we have two types of latent heat, LF and LV. LF stands for latent heat for fusion, where it's involved melting process, normally from solid to liquid, right? And LV is the latent heat for vaporization, okay, where we have liquid become gas. Okay, so if we want to calculate the amount of the Q involved in latent heat process, the Q is equivalent to ml, and m is delta m. For example, if we have these 3 cubes of ice, okay, so initially we don't have any mass of water due to the ice here, but after the ice completely melted, the m final of the water from the melted ice will be increased. So we have changes in terms of mass of the water, okay, due to the melting process of the ice. That is why the m here must be delta m. Okay, so the Q will be varied according to the amount of the substance. For example, for 3 ice cube in comparison to 1 iceberg like this, okay, of course the Q will be different. This will be huge or large amount of heat needed. Okay, so here is the table 19.2. We can observe different value of latent heat of vaporization and also latent heat of fusion. The common process that we all experience in our daily life is about process of heating up ice, okay, melting it, and then high increase in temperature of it, and until it reach boiling point, where it's going to convert or become steam and completely become steam, and finally the steam is heat up. Okay, for process A here, from negative 30 to 0 degrees Celsius, we do observe change in temperature. So the Q needed or add up to process A is MC delta T. So the amount of it is this one. For process B, from at 0 degrees Celsius, the process stagnant or static at 0 degrees Celsius. There is no increment of temperature. Therefore, here we have a melting process. For process B, the Q is mLF. This is the amount of the Q transferred into the ice. Okay, and then for process C, we do have increment of temperature from 0 up to 100 degrees Celsius. So for process C, the formula is MC delta T. So this is the amount of the energy add up to the system. So the Q is positive, yeah, because it's add up to the system. If it is taken out, then it will be negative. For process D, okay, at 100 degrees Celsius, the boiling water start to convert itself into steam. Okay, so for this process is mLV. Okay, so huge amount. Okay, huge amount of energy needed to change the water, the whole of the water, totally become steam. After it reach steam point, okay, here we have process E. The steam is heat up. Again, we are going to observe changing in temperature. So the formula for process E is MC delta T, which is 40.2 Joule. If we need to calculate the Q total involved from A up to E processes, then you have to add up everything. So this is the whole bulk of the energy needed, okay, to be transferred into the ice from negative 30 degrees Celsius to become or completely become steam and reach temperature of 120 degrees here. Okay, supercooling is a process or phenomenon whenever we have liquid water is held perfectly still. It must be perfectly still in a very clean container. It is possible to have water to drop below 0 degrees Celsius, okay, without freezing into ice. This phenomenon is known as supercooling, arises because the water requires a disturbance of some sort of molecules to move apart and start forming the large open ice structure that makes the density of ice lower than of the water as discussed in section 18.4. If the supercool water is disturbed, it suddenly freezes. Okay, the system drops into the lower energy configuration of bound molecules of the ice structure, like this. Okay, and the energy released raises the temperature back to 0 degrees Celsius. So this is commercially used as the hand warmers. Example 19.4, okay, cooling the steam. What mass of steam initially at just 130 degrees Celsius is needed to warm 200 gram of water in 100 gram glass container from 20 to 50 degrees Celsius. So in this case, we are going to use conservation of energy, or Q cold equivalent to of negative of Q hot is the same thing, right? Because it's coming from Q cold plus Q hot equivalent to 0. So rearrange of this, you will have Q cold equivalent to of negative of Q hot. So in this process, okay, the steam undergoes three processes. Okay, three processes. Okay, first, okay, a decrease in temperature to 100 degrees Celsius. Okay, because it's starting from 130, at least it need to cool down, okay, to 100 degrees Celsius, where we have here Q1 as the first process. Okay, and then the steam going to have undergo condensation into liquid water, okay, which is Q2 condensation, and then finally a decrease in temperature of the water to 50 degrees Celsius. Okay, so Q1, Q2 and Q3 is a process for the Q hot, which is the process for the steam, right? The one that cold is actually the water and the glass, because we know it's 20 degree to 50 degrees Celsius. So both of this is MC delta T, formula of it. So, okay, by make use of Q cold equivalent to negative of Q hot, okay, so what is Q cold? We have two elements, the water and the glass. What is the Q hot? Three processes just now, okay, decrement in temperature or cooling down for the steam, vaporization process, and then cool down from vaporization process to hot water. So our unknown here is M steam. So rearrange this equation, okay, you will have like this. Substitute everything accordingly, you will have 10.9 gram of steam needed to do this process to warm up water and glass from 20 degrees Celsius to 50 degrees Celsius, right? What if the final state of the system is water at 100 degrees Celsius only, not up to, okay, 50 degrees Celsius just now? So 30 of cold water, okay, it's not 30 degree, it's going to be 80 degree, okay, because 100 minus 20. Delta T of the hot water, 0. Substitute this information again into this equation, you will get mass of the steam is 13.7 gram.